Hey subscribers, welcome back to another episode of Science with Surback. Today what we're going to be talking about is the introduction to the electron. Remember, up to this point we've talked about the nucleus, the protons and the neutrons, and we've talked about what happens when the nucleus gets affected. Well, now what we're going to talk about is the electron. And we'll get into this business here in just a second. First, I want to go over the objectives for this particular unit. So we have quite a number of objectives, but the first objective is describe the wave properties and characteristics of speed of radiant energy or electromagnetic radiation. Objective number 2, use the relationship described by the wave speed equation to calculate wavelength, frequency, or radiant energy. Objective number 3, explain the essential feature of Planck's quantum theory and use the equation energy is equal to Planck's constant times the frequency. Objective 4, explain how Einstein accounted for the photoelectric effect by considering the radiant energy and stream of quantized energy packets or photons by striking a metal surface. Objective number 5, explain the origin of line spectra. Objective number 6, list the 3 postulates made by Bohr in his model of the hydrogen atom. Objective 7, explain the concept of an allowed energy state and how this concept is related to quantum theory. And that is our final objective here. Now, as we get going here, there are a couple of things here to remind you of. Number 1, you need to copy down what I write as well as the highlighted words that are written in red and highlighted in yellow. Now, we start off by talking about electromagnetic radiation and specifically about waves. And you may be thinking, hold on a second, we're talking about the atomic structure, right? We're talking protons, neutrons, and electrons. So why do we take this step back and talk about waves? Well, I won't say it was easy for scientists to go through experiments to talk about protons and neutrons and figure out business about the nucleus, but it was discovered prior to this business about electrons. And there was a couple things about electrons that were odd and hard to figure out. What we have to remember is this. At this point in time, before we've really gotten to the details of electrons, we have the Bohr model of the atom. So remember, with the Bohr model, we had that nuclear model where we had the protons and neutrons in the nucleus, and then around the outside we had those particular electrons. Now, the Bohr model did a really good job about depicting what happens with that nucleus or where it's at, and that was through the Rutherford model of the atom. And we still really hadn't figured out, okay, the electrons, yeah, they're around the atom, and so we have to know a little bit about electromagnetic radiation, or you can just think about this as quote-unquote light. And light had a lot of wave characteristics. Now, the reason we're doing this, and I should have just started off with this, but the reason that we're doing this is that we can use information on light to help explain electron behavior and characteristics. So let me pause and write that down. So again, we're going to use light to help explain what's happening with electrons. So again, a lot of this work is taking place in the early 1900s. A lot of the well-renowned physicists that we know are doing a lot of work on this. And again, these are just some basic definitions to be familiar with, because they knew at that time that light had these wave characteristics. Well, because it had these wave characteristics, we could calculate the speed through this formula where we take the wavelength times the frequency. Now, we're going to use the speed of light at 3 times 10 to the 8th meters per second. And then we're going to use these quantities here for wavelength and frequency. Again, why we need to know this is because we're going to use light to help explain what is happening with electrons, or to help explain those characteristics. So what we do here is we get into the electromagnetic spectrum. Okay, so the electromagnetic spectrum is accounting for all light. Now, when I say light in a science perspective, particularly a physics and chemistry perspective, I'm including everything that is from, you see here, gamma rays, all the way to radio waves. Now, what we typically think of as light is this tiny little sliver known as the visible spectrum, because that is what we can actually see. Electromagnetic radiation is going to deal with any light that moves in that wave-like particles, and we've done a lot of work to emphasize this. All right, so to help understand a little bit more about light, we need to go through some example problems. Okay, so our example problems here. We have our electromagnetic waves, and what I'm referring to is these pictures down in the lower left, and it says which wave has the higher frequency. Well, you guys can probably identify this, but remember, the frequency of the wave is going to talk about the number of cycles that pass a point in 1 second. So what I'm saying is, which one of these two pictures has the most waves? Well, picture B has the most waves. There's the most cycles, or the most up and down motions going through this portion here. And then it says, if one wave represents visible light and the other represents infrared radiation, which wave is it? And again, you can reference that particular picture that is in your notes, but listen to this. Your visible light has a wavelength of about 400 to 750 nanometers. And infrared radiation is just to the right, and the wavelength is getting a lot larger. Okay, so what we're saying, infrared is going to have a lot larger wavelength. So you check this out. The wavelength here for wave A is much larger than wave B. So again, wave A is infrared, and the reason for that is that it has a larger wavelength. Wave B is visible light, because it has a smaller wavelength. And then we use our equation here. It says the yellow light given off by a sodium vapor lamp has a wavelength of 589 nanometers. What is the frequency of this radiation? Well, remember, we're going to use C equals wavelength times our frequency. And so C, we are going to use 3.00 times 10 to the 8th meters per second. Our wavelength is given at 589 nanometers. And then our frequency is what we are going to be solving for. That's going to be our question mark, okay? So The thing that we need to do first is we need to convert nanometers into meters. So again, our wavelength here needs to be converted to meters. And so the way we do that, remember, there is 1 times 10 to the 9th, 1 times 10 to the 9th nanometers in every 1 meter. Okay? So when we plug that into our calculator, we get a value of 589 divided by 1 times 10 to the 9th. And we get a value of a lot of decimals. I don't want to deal with that. And so I'm going to put it into scientific notation. So the number of meters here is 5.89 times 10 to the negative 7. And that would be in meters. So now that we have those values in the same unit, we can plug this back into our equation. And so we would set our speed of light equal to 5.89 times 10 to the negative 7th meters times our frequency. Okay, so we need to get frequency by itself. We divide each side by 5.89 times 10 to the negative 7th meters. And when we do that, we get the following. Again, we're going to take our 3.00 times 10 to the 8th, divide it by 5.89 times 10 to the negative 7th, and we get a value of, when we round to, we could believe this as 5.09 times 10 to the 14th hertz. So again, that is 5.09 times 10 to the 14th hertz, or if you want to use inverse seconds, either way, that is a correct unit for our frequency. The big thing here is make sure that your units for either your speed of light or your wavelength is converted correctly. So again, the reason we introduced this early on here is because we need that concept of light to help explain the characteristics of electrons. All right. So now we get into this business here. We can get a little bit closer to explaining why we use our light to help explain our electrons. Okay. So what happened was this. Again, they had the work on the nucleus, and they were beginning to question some things about what happened. And so there's 3 very, very unique things, and we'll get into details of these throughout this process in notes. But the first is blackbody radiation. And simply this is thought of, or this can be thought of, as taking a metal object and heating it up, such as steel. So like I was saying, blackbody radiation is essentially you heat an item up, it gets a different color from that heat exchange. Now the photoelectric effect, it says it's the emission of electrons off a metal surface. And then the emission spectrum is you have these electrons getting excited, quote unquote, and they get emitted to a different energy level. Now, I talk about each of these in detail, so we'll go through this example more in depth. But we move here to blackbody radiation. And the best way to describe this is that red hot heat when you heat up a metal object. So say, for example, you have a sample of iron. When you heat iron up, it will turn red. What happened here, you can see Max Planck, is he knew, okay, as you heat this iron up and it turns red, there's a color change associated with that. Well, he knew a little bit about light, and he knew as you change that color, you're affecting the wavelength, and ultimately the frequency. So what he did was he said, okay, I know this is changing colors, and I know that I can associate properties of waves associated with colors. Can there be an energy that I can correlate to this? Because he knew, hey, you're heating it up, there has to be some sort of transfer of energy. And so what he was able to develop was a mathematical formula to be able to describe this phenomenon. Now, what he described this as is called quanta. So basically, he said that energy can be absorbed and released in certain amounts of energy, okay? So now they're starting to correlate with Max Planck here. Now they're starting to correlate, okay, how does light, electromagnetic radiation, how can this be used to explain what's happening here with the electron? So again, they knew something was happening with that atom. Because they could correlate it to light, that was their best way to go through this particular example. Now, we'll go a little bit more in depth in this quanta because that's a really important concept, and it's really important to use this formula of Max Planck to be able to explain that. So when Max Planck found this quanta, found this energy change was absorbed and released in these certain defined quantities and in these very small amounts, he not only associated it with a formula, but he saw that there was very specific energy changes that occur. So what he did, or the best way to describe this, is a set of stairs. So as you move upstairs, you're moving up a certain height, and hopefully the stairs are built correctly, and so you're moving up the same height as you move up the stairs. And so basically what he found was that as the energy was adjusted, as he heated some object up, he noticed there was, again, these very specific defined energy, and that energy was very systematic where it was. And so what this is saying here is that, again, as the energy is absorbed and released, it's released in very specific amounts, okay? So we before we move on here, just to summarize this, blackbody radiation, again, an object's getting quote-unquote red hot. They knew a color change could be associated with that light spectrum, and they knew they could associate quantities of wavelength and frequency. What Planck did is he went one step further and he found out how much specific energy was being absorbed and released in an object that got heated up. The next concept here is all about Albert Einstein and what he did here. Again, I'm going to say this and I'll pause. The important thing about blackbody radiation is it's the first time that they correlate wave-like characteristics or light characteristics to atoms. So again, the big key takeaway from this is atoms and electromagnetic radiations are going to be correlated. In other words, atoms in some way, shape, or form, we'll later learn electrons specifically, have wave-like characteristics, okay? So, we get to the photoelectric effect, which is all about Einstein. And so, what Einstein does, I really just summarized this here, is that it says, hey, there is a minimum of frequency to eject these electrons, or to emit these electrons. And so what that means is that for light, it has to have some particle nature. Now this is really significant moving on down the road because, it's going to help explain the business about electrons. So again, with this, what he did was this. They knew that light behaved as a wave, and they could use that to help explain some things about the atom. And then what they did was they shined this light, a specific frequency of light, and it hit a metal surface and it ejected these electrons. Well, think about this. If you have something like wind blow through your hair, it's going to need to pack a punch to be able to, again, blow your hair in multiple different directions. So I know that that's not a very good example, but what Einstein did here is he said, hey, I'm just shining light onto this metal surface. The only way I can get these ejections of electrons is if they pack a punch, or if they transfer their energy, and they have to transfer their energy via a particle. So basically it's taking what Planck did about blackbody radiation, and he says, hey, light moves as a wave. Einstein takes that one step further and says, yes, light has to move as a wave, but the only way to pack the punch is it has to also behave as a particle. So this right here, I'm going to write this down, is known or finds that light has a duality. Okay, so again, bottom line up front here with the photoelectric effect, light is considered to be duality, both wave and particle in nature. Now we get to the detailed understanding of the photoelectric effect. Again, light shining on this metal surface will cause electrons to be ejected only if it has sufficient energy. Okay, so what that means is that this needed a high enough frequency. And so that's what it's talking about, above and below this particular threshold. Now, you may be wondering, all right, we've spent 2 sections talking about light, and we get it. Yes, light has a blackbody radiation. This can be explained through those wave-like particles or characteristics. It also has a particle-like characteristics because it's able to pack that punch. It's able to kick those electrons out. How does this correlate to atoms? Well, let's tie this full circle now to light and atoms. So we start out here with line spectrum. And line spectrum here is defined or produced when radiation of light is separated into its different wavelength components. Now we have 2 different types of spectrum that we need to be aware of. One is a continuous spectrum. So if we're looking at a continuous spectrum of light, we're going to see all colors of the rainbow. We're going to get the entire visible spectrum. Now, a line spectrum is only going to be the specific wavelengths that we can see. So a line spectrum here, I should have labeled these pictures, but a line spectrum is on the left, and on the right, this rainbow here is a continuous spectrum. Okay, so how we identify our particular atoms is going to be through these particular line spectrum. Again, as something heats up, or as something more specifically gains energy, it is going to emit that light. Just like when you heat that metal object up and it gets red hot, as you heat or excite or energize an atom, it's going to give off a light that's a unique footprint for each and every atom. So here is what we have here. We have 2 different types of spectrums that we are going to be specifically dealing with. We have the emission spectrum and we have the absorption spectrum. Now, for us in this class, typically we're going to see the emission spectrums. So this is the set of frequencies that is emitted as an atom is in an excited state. So I want to clarify this here. An excited state is just saying, hey, energy added. And you can think to yourself, okay, energy added to a particular atom is giving us that business that Max Planck defined here, or that Max Planck went over. So this light is going to be caused when energy is released in this particular fashion. Now, the absorption spectrum is just the opposite of the emission spectrum. So these lines of light are going to be absorbed, as the definition says here, by that sample. So these two are the same exact sample. And so you can see in an emission spectrum, you just see the lines of light that are emitted, where in an absorption spectrum, those lines of light are absent in that continuous spectrum. Again, they are a perfect correlation of one another. So, again, two things here are very, very important. And as we'll see in the next example, it ties everything together. To give off this spectrum, either an emission or absorption spectrum, there has to be some emission of light. Again, atom has to be correlated to some wave-like characteristics. To pack energy, it's going to have that particle business here. And that's that duality business that's used to help explain the details of electrons. Okay, so now, if you haven't been paying attention, I would definitely pay attention for what's going to go on now. So, again, we spent all this time talking about this duality of light. What's the so what? We're supposed to be talking about the atomic structure. And here it is, all right? So what they learn about light, about how it packs both a particle and a wave-like characteristic all in it, is this. When they add energy to an atom, it gets excited. It emits this light. We already know all this business about light, and so now we can say, okay, what we know about light, we can start to correlate to the atom. A key thing here was this. We knew a lot of information at the point in time about the nucleus, the protons and neutrons, and we knew that, hey, around the nucleus, somehow there's these electrons. And these electrons were going to be at these specific energy levels. Okay? So, again, yeah, they're around the nucleus, but they're in these regions. And what happens here is that as energy is, again, emitted or absorbed, these electrons move from one state to another. Okay, and so here is another important point here. This energy gained or lost as a photon. Again, quote unquote, the particle nature of light. So what they're saying is that, hey, as these electrons jump up and down energy levels, which we'll get into those energy levels more specifically as we get on into this further into this unit, they're going to emit light. Okay, so light already has those wave-like characteristics, and then because they lose and gain this energy, the electrons also have to have this particle nature that is explained through light. So again, what I said from the very get-go of this section is that, yes, light has that duality of particle and wave-like characteristics, and this is going to be used to help explain electrons and their behaviors. So let's get more specifically here. Again, we're using the Bohr model, which, remember, had the center of the nucleus and then those rings, quote-unquote, those orbits where those electrons are. So they say, okay, well, all right, that's great. These electrons, they're going to gain and lose energy, and they're going to gain and lose energy, and as they do that, they're going to emit this light, which we can see. It's like a unique footprint. We can see that emission spectrum. And because they emit light, we know that light itself is going to have that energy or those particle properties associated with it. And so what happens here is that as electrons move between energy levels, they're going to emit light. As light is given off, we can correlate all of those things that we've learned about light in terms of the business that we just discussed this whole section. All right, so great. Now we have this way to explain the characteristics and behavior of electrons. However, when they go to try to apply this particular theory to anything but hydrogen, the system fails. And where it fails here is these perfect circular orbits. All right. What happens here? Again, the Bohr model of the atom and the business about electrons can be perfectly explained by that business we know about light. However, when we go to try to apply this particular business back to any other atom except for hydrogen, it doesn't work. We can't explain it. We get these too many lines. We get too many things that we can't explain. And so the major takeaway here is, because his explanation can't tie together everything from helium on, this right here, this actually should be starred. What this does, the business about light and Bohr's model says, hey, electrons do not move in circular orbits, okay? Really what this is saying here, we need a new model of atom. This is too old school, and it can't explain what we know about light, which we can help explain about electrons. Really big things here is that electrons have energy that is quantized. So they move in specific amounts. Now, energy gained is moving to that higher energy level. Energy lost is when an electron moves to a lower energy level. Again, you have the movement of electrons, which explains why we get this nice emission spectrum for each and every atom, each and every compound, in fact, and we get this energy that is quantized. So again, the big takeaway here is that, okay, the business about light can help explain electrons. We know from the model that it could explain what happens to hydrogen in terms of the Bohr model. However, because the model fails in explaining every other atom, we need a new model. So big takeaways here really were those last 3 pages of notes that I showed you. Again, energy is gained or lost in those it's quantized. It's gained in those quanta. Electrons can move in between energy levels. However, right now we need a redesign of how we view those particular energy levels. All right, so this kind of leaves you in a cliffhanger. I know you're just jumping for joy to learn some more. We will do that in the following section of notes. And really what we're going to do is, I know we had a lot of theory, a lot of far out information here. We're going to bring it all together, tie it all together, and talk specifically about the details of electrons. I know you're excited because I am too. I hope you have enjoyed this particular episode. And as always, if you haven't done so already, make sure you subscribe.